Hello, everyone. Welcome to the first session of the IGRM for 2021, hosted by the Department of Geography at Mary Immaculate College. I hope that the video and audio is working for YouTube. If someone who is in the YouTube link might like to send a message or something in the chat, just to note if you can hear us properly, that would be appreciated.
It works actually. I just checked on YouTube.
I can see that the video is working, but I'm not sure if the sound is working properly yet.
Yeah, the sound too, I think.
I mean, I'll try. I'll see if I can mute.
Excellent. Thank you to the couple of people there who have confirmed that the sound is working. Thanks very much to everyone for joining this morning. I'm sorry, of course, that we can't be welcoming you to Limerick, to Mary Immaculate College in person. Hopefully, we'll get that opportunity in a few years' time. But I'm glad that we're still able to run an IGRM this year. This morning now we have our first session, so I'm going to pass over to our session chairs, Tiernan Henry and Finney Papageorgiou.
Good morning, everyone.
Hello.
I suppose we thanks for that introduction, Brendan, and I suppose our first online IGRM, a whole new take on how we do this sort of stuff. So I suppose we might as well get started. And we've three talks in the first session. Finney, do you want to introduce the first one?
Yes. Hello, everyone. So our first talk would be given by Jim Hodson, and he will give us a TELUS program update and new old data. So Jim, whenever you're ready.
Thanks very much, Fanny. I'll just share my screen. Hopefully you can see that.
Yep.
Thanks very much for the invite, and I'm delighted to start off this 64th IGRM. And actually, before I start, I'd just like to say a well done to Brendan for putting this together, having an IGRM this year, the first virtual one. It's actually over 20 years since I first attended an IGRM back in Galway a long time ago. And it's always one of my favourite conferences to attend, to find out kind of what's going on in the geological world in Ireland, but also to meet up with old friends. And hopefully next year we'll be able to do that again in person. So I'm just going to give you a quick update on the TELUS programme, what we've been up to over the last sort of 12 months or so, the activities we've been doing. I'm going to touch on COVID. Obviously, it's been has a massive impact on ourselves, but obviously everybody. And then just looking ahead, sort of our plans for this year. We're also pleased to announce some more new old data, which I'm calling it, so a new data release, which is kind of the data going out today, and a few other things just to look out for later on in the year. So I'm sure most people have heard of TELUS. I hope people have. But for those who haven't, TELUS is a kind of an airborne geophysical and ground geochemical mapping project. It's managed by the Geological Survey Ireland, and I'm very biased, but I think it's a really exciting kind of project to be part of, and I'm really looking forward to the chance when we can actually produce all island maps of sort of geophysics and geochemical data. It's a really interesting and great project to be part of. And just to say that it is actually directly funded by our main department, the Department of Environment, Climate and Communications. And just a bit more detail on the actual surveys we carry out. We do a kind of airborne geophysical survey. So we collect 3 different types of data: the magnetic field, so ground conductivity, natural gamma ray radiation. And this is all collected from an aircraft flying very low at about 60 meters above the ground. The survey is done by a Canadian company called Sander Geophysics, and there's a large part of kind of communications involved in both the Airborne survey and the Geochemical survey. So we take make a big effort to make sure we kind of have the minimum disruption to people and let people know when we're flying or when we're out in the fields. From the ground Geochemical survey, there's actually three main types we're collecting. So we're collecting soils, we're collecting stream sediments, and we're collecting stream waters. And so we have sort of pairs of samplers who go out into the field collecting these samples. Once we collect them, they're obviously then sent to a laboratory to be prepped and analysed further on. And then hopefully we produce geochemical maps, typically about sort of 50 odd elements of different geochemical elements. Also, I must actually add, we're not just doing sort of surveys. We have now kind of a third strand to the geophysical program, to the TELUS program, which is a kind of what we call applied products. So where we take the data we collect and do something useful with them. And I'll touch on that later on. So 12 months ago, we were sitting in a wet and windy Athlone for the IGRM. And there we actually released the latest kind of geophysical data we had, which was for the Southeast Island. This is the image you can see on the right-hand side. That's a magnetic map of kind of over Wicklow and Wexford. And we were also able to release kind of some data, sort of some EM inversion data from Limerick. This is data, this is the ground conductivity data, which has then been inverted using some MP software, which was developed by Dias, which allows us to produce kind of data in sort of sections and sort of depth sections. And we've continued to do more of that, and we've released more of that data last year in July over Cork and Waterford. And we were also delighted last sort of October to release some of the geochemistry data. This is the sort of the topsoil soil geochemistry ICP data for the North Midlands. And this meant that we'd had actually collected 50% of the country. So we're making progress. Obviously, COVID had an impact during the year, but we did manage to get some survey fieldwork carried out. But it also gave us an opportunity to develop a new digital data capture system. This was for the geochemistry. So we've been collecting our data, so filling out sort of field cards, using our maps, but we've now integrated that all into kind of a tablet, a digital data capture system. And I must actually thank sort of Judith Mather and Peter Heath for kind of driving this and getting it up and working. And we've managed to get out and sort of start collecting this data. And it's made it a much more efficient, much more kind of a modern survey we're doing now. And it's worked really, really well. So I'm delighted to see that up and running. As I said, we did actually get out to survey this area. So on the map there in the middle, you can see a kind of a green hatched area. This is the survey area we were carrying out last year. Unfortunately, we had a number of lockdowns, which sort of we had to stop sampling. So we've got about 60% of that area covered. For the Airborne survey, we carried out a sort of a survey, what we call the kind of A8 survey block, which is covering kind of Tipperary, Kilkenny, the kind of the area to the west of where we surveyed last year. And due to the late arrival of the plane, again from kind of delays from COVID, we're only about sort of 50% complete. We were based down in Waterford for that survey, so we managed to get a good bit done, but we planned to start the survey in April, but it was actually the end of September before we managed to get going. So hopefully we'll get some more done of that. But also last year, we also took the opportunity to release a number of different reports and outputs from different projects. So the geophysics team put together an interpretation guide to airborne geophysics. So this is taking the TELUS data and using how to use it for geological interpretation. All these books and reports are actually on the GSI website on the TELUS pages under publications. So have a look there for these. We also produced a report with our colleagues in the Environment Protection Agency and Trinity College, looking at how the airborne radiometric data can be used for kind of radon risk mapping. And one of the other projects we were happy to release last year was a kind of a geochemical characterization of appropriate levels for soil recovery facilities, which is a bit of a mouthful. But basically what this is if you've got a development going on, or a sort of site investigation, you're clearing out lots of soil, and where does that soil go to? And is the place that's receiving that soil suitable geochemically to receive that soil? So it was a report done with the EPA, which was published last year, which is a really useful piece of work. So I said, please go to the website to look up if you're interested in any of these reports or any of the activities. We'll have them all listed there. As I said at the start, COVID had a big impact on all of us. Last March, we were all sort of told to like, let's all work from home, which at the time seemed like quite a novelty and kind of quite a good thing, but things may have changed over the last 12 months. And obviously this has had impacts from the way people have worked, and I must admit the TELUS team have done a great job of kind of just getting on with it and working well. But obviously it's had really big impacts on the field side of actually carrying out field work. Particularly in the current situations where we have lockdowns, we just can't get out and do any field work. We've had to change the protocols of how we do things. Simple things have made a big difference to how we can actually operate. So obviously maintaining social distancing when we're out on the field, sanitizing gates as we walk through them. But things like we now need to have a vehicle for each sampler. So from previously, we only needed sort of 3 or 4 field vans. Now we need maybe sort of 6 or 8 field vans. So obviously that causes difficulties. Asking people to wipe down kind of the tablets that they're using in the field, wiping down the augers. It all adds kind of to the time and causes delays when you're actually doing the work. As I said, with the Airborne survey, that had a big impact on us. The main problem was actually getting the aircraft into the country. The aircraft was actually, and the company are based in Canada, and normally it's only a small aircraft. So normally they fly in a series of hops. So they fly up to northern Canada, hop over to Greenland, to Iceland, and then down to ourselves. But they had big problems of actually even being allowed to land in Greenland and Iceland. And it took months and months before they actually got permission to land in Greenland. The Greenland authorities allowed them to land and refuel, but the pilots weren't allowed to leave the aircraft. So it did cause a big delay in actually getting the aircraft here. And as I said, it wasn't until the end of September when we started surveying, which was kind of months after we'd initially planned. And of course, there was other issues. A lot of things related to contracts with our contractors. We had sort of fixed time when we were meant to get the surveys done. And obviously we had to do kind of contract exchange. So it was just an increase in kind of the amount of red tape and admin associated with those. But I suppose what we've learned from that is obviously there's been delays and disruptions, but we need to kind of have greater flexibility and sort of patience, both from ourselves and also from the contractors we're using. And hopefully, I think we'll have to bring those kind of lessons into kind of our plans for this year in 2021. So this is just what we're planning to do for the Airborne survey. And on the map on the left-hand side, the dashed area is the A8 block, which is about 50% done, which we hope to finish off this year. The aircraft is currently undergoing maintenance. Unfortunately, they can only be carried out by Canadian engineers, and even getting the Canadian engineers into the country is causing a difficulty. But hopefully we'll be back up flying fairly soon. Once we've completed that block, we'll then move on to the dark blue area there, which is over Cork, and get that completed. And they're also planning to undertake what we're calling a master grid. I've noticed a spelling mistake, so excuse me there. But this is be like a baseline survey over the whole of the country. This is actually quite not finalised yet. We might have to remove some of the lines over Northern Ireland. But the idea of this is to tie in all the previous survey blocks into one master grid to allow us to kind of correlate the data. For the geochemistry survey this year, and our plans are again to the green hashed area to the south of Dublin, covering kind of Wicklow, Kildare, sort of Laois area. Finish that area off. We're about 40% left to carry out. The dark blue is an urban soil sampling survey we're planning to carry out once we've done the first area. This is the same kind of sampling we do across the whole of the country, but it's going to be done at a higher density. So we'll be taking more samples. And then finally, hopefully all going well, we're going to carry out a further sampling in the Southeast Island, again, soil sampling. The aim of getting sort of soils completed for the whole country over the next few years. And once we've collected all these samples, they'll then obviously be sent to the lab for prep and analysis, and hopefully we'll have some more data releases later on in the year and next year. As I mentioned earlier, we're not just about sort of collecting survey data, but obviously that's what the starting point. We've also, my colleague Murray Glennon is kind of leading on this, is kind of developing kind of what we're calling applied products, usable products that takes the kind of the TELUS data and does something useful with them. And effectively, there's 5 main areas where we're working in this, and this is kind of health, environment, minerals, agriculture, and climate. So under the health, I've already mentioned about sort of the radon risk mapping, which we've been doing with kind of the Environment Protection Agency and Trinity. But it's also kind of looking at kind of the chemistry. Some of the projects we have with UCD has just finished up recently on sort of biosolids and metals. So there's a range of different areas we're kind of working in. Under the environment kind of banner, one of the projects we're starting off this year is what we're calling the Boulder clay geochemical characterization. This is a follow-up on the soil recovery facilities work we did previously. And again, it's taking a kind of a more detailed look at the geochemical characterization of the Boulder clay in Dublin.
Jim, we've also, 2 minutes, sorry.
All right, I think I better speed up then. We also look at kind of different pollutants, and we're doing some work on exploratory data analysis of the water geochemistry data. Just a couple of the other projects we've been working on this year. So from a minerals prospectivity project, we're doing this with the minerals section in the GSI. And again, this is to kind of produce, hopefully by the end of the year, kind of taking the TELUS data and some exploratory data from mineral companies, putting it all together and looking at kind of where are sort of prospective areas for mineral exploration. We're also continuing our work with TerraSoil, which is a joint project with Chuggas, looking at kind of soil fertility, and obviously a number of other areas looking at sort of carbon sequestration under the climate banner and soil. But I'll move quickly on. I just want to announce kind of a couple of new data sets we have. So this thanks go to Vincent Gallagher here for kind of looking down the back of his couch for some old data. So he found sort of 514 rock samples collected between the 1970s and 1990s, which are analysed by a number of different methods. It's a really useful data set. He's put a report, and the data is available from the TELUS pages on the GSI website. So please have a look at that. Also, it's not the only data Vincent found. We also had some new lithium stream sediment data. So this was from about sort of 1,884 samples collected in the 80s and 90s, which is kind of now again sort of available online on the TELUS website. And this is actually a really useful kind of data set, and I think we'll have a lot of interest to it. A number of different people, particularly some of the kind of EU projects, the GEO-ERA projects. Frame is one of them, which looks at kind of the raw material needs within Europe. And lithium obviously is a kind of an interesting element for that, with kind of the need for developing batteries and so on. So, and I know other people, kind of Julie Manouge's group, are looking at kind of lithium in sort of the Southeast Island. So again, it's an interesting data set, and often a lot of this work starts with data, and we can do good research if we have good data. So again, go on to the website to look at and download that data. Just a couple of things to look out for later on this year. It's actually 10 years since TELUS started in the Geological Survey Island. So we're going to have a seminar later on this year to kind of look back at some of the data we've collected, some of the projects and the research we've been involved in, and we'll give some more information of that as the year goes on. We also have we're going to be updating the website, adding to kind of our story map, Tales from TELUS. And also, just if students are interested in using our data, whether it's the geophysics or the geochemistry, or have sort of final year projects or research projects they want to work with, just please get in contact with us, and we can talk about that. And just very finally, the GSI are kind of really pleased to announce that we're looking for 6 new graduates. These are geological graduates to work in the GSI. So every year we have a competition to take on 6 graduates to work in each of the sort of different sections. So in TELUS, in the marine and coastal units, in minerals, mapping, groundwater and heritage. The deadline is actually the 15th of March. So check out the webpage to get some more information. It's a great opportunity. I think anybody who's actually done one of these graduate positions before, it's an 11-month contract. I've really felt the benefit of it. And it's actually been a great a great program both for the Geological Survey and also for the graduates. So I kind of advise you to kind of check that out. And I'll finish up there. I just really want to thank kind of the TELUS team who have done such a great job over the last 12 months, and also all the kind of the contractors who we've been working with. So thank you very much.
That's great, Jim. Thanks a lot. We'll take questions from people, I suppose, on YouTube. And Michael Dempster's got one, Jim. Is the TIL project using direct TIL sampling or proxy data?
Sorry, you just broke up there. Can you say that again?
Yeah. Is the TIL project using direct TIL sampling or proxy data?
It's not really TIL, it's soil sampling, I suppose. So I'm not sure what he means by the TIL project.
Michael, if you want to type in there, we can clarify that. So Jim, while you're there, can I ask you a quick question? You know, it's 10 years old. Do you think, would you be interested in going back to the border and redoing the border?
I think the priorities obviously is completing the country, which there's still a number of years left in that. The Airborne is still probably going to take another 2 or 3 years. The Geochemistry a little bit longer to get that done. I think after that, the focus will probably be on more local level, kind of smaller scale surveys. So there's obviously areas of interest. Depends if it's just from a sampling and kind of collecting data, maybe not going back and doing those large scale regional surveys, but more focusing on sort of smaller scale. But there's always interesting research that can be carried out in those areas. So, well, I say if people have plans and proposals or kind of suggestions, we're obviously open to hear about those.
Okay. Well, there's no other questions just at the moment. So I think, Jim, we can return at the end of the three talks anyway, in case people want to get back to us. And again, if people want to just use the chat, they can type in questions and we'll get to them at the end of each session. Listen, thanks, Jim. That was really interesting. Sorry. Yes, sorry, Jim. Clarity. Yeah. You referred to characterizing the Boulder clay in Dublin. That's what Michael was referring to. So,
okay.
Yeah.
So this is from, I suppose, from a site investigation point of view. So what we're actually looking for at the moment is we've sent out a request to consultants who've been working kind of effectively in Dublin in a lot of the site investigations, and asking for them to send back kind of information, geochemical information about the sort of the sampling and the logs and the cores they've done over the years. And we're going to kind of look at the boulder clay and the variations within that, because it's not just one unit, it's quite varied across Dublin. And again, looking at how that data is then from a site investigation, geotechnical investigation point of view, how it's extracted, and then what is the geochemical signal of that and what to do with it. Can you just remove the Dublin boulder clay and remove it to a kind of a recovery facility, or does it have to be more kind of varied than that and go to different areas? So it's trying to get a better understanding of the Dublin boulder clay from a geochemical point of view.
Great, thanks. Okay, Finney, over to you.
Yes, thank you, Jim. So our next speaker is David O'Leary, and he's going to talk about the potential of self-organizing maps clustering to characterize harvested peatland using airborne radiometric data and a digital elevation model. So over to you, David.
Thanks very much, Fanny. Can you see my screen?
Sorry.
Yeah,
yes.
No problem.
Yeah, okay, good to go. So yeah, hello there everyone, and thanks for giving me the opportunity to present my work. My name is Dave O'Leary, and I'm a third-year PhD student at the Department of Earth and Ocean Sciences at NUI Galway. My PhD is all about using large, free national data sets to try and solve problems at a scale that is useful to people. In Ireland, we have an unusually abundant number of national data sets, such as the bedrock and quaternary geology maps, soil and radon maps. And as we've seen from Jim, we also have the TELUS survey. And of course, with the recent advent of satellite data from the ESA and NASA, I think we really have a unique opportunity to become leaders in the field of big data for local problems. With that in mind, I'm going to present some of my work using the TELUS data to divide a peatland into areas of similar peat. And this is a project, or this is a collaborative work with the engineering department in NUI Galway. So peatlands are important as they contribute to many ecosystem services such as drinking water, biomass production and flood retention. When peatlands are drained, negative environmental impacts include reduced surface water quality, loss in biodiversity, and greenhouse gas emission. Conversely, restored peatlands can return sites to being carbon neutral or even carbon negative. And this has the potential to play a large role in a country's overall environmental targets. And it was sort of recently recognised by the Irish government with an injection of funding into peat restoration via Bord na Móna. The Water Peat project is a European level JPI with the goal of water management for sustainable use and protection of peatlands. This project is led by the University of Oulu in Finland with input from the NI-BIO in Norway and NUI Galway here in Ireland. Here in Galway, of course, the Water Peat team focused initially on the analysis phase and have taken cores from a peatland site to the lab. Before all this, however, they faced the problem of where to core, as these peatlands are often vast, and knowing where best represents the site is difficult, if not impossible, with some form of ground survey. Geophysics potentially offered a way to help with this, so our research group joined the Water Peat team, and this study was born. Previous work, both in Ireland and abroad, have used either radiometric, electromagnetic, or some combination of the two to provide estimates of peat extent and peat depth. So I started by researching these methods. As we've seen, of course, the TELUS survey measures such geophysical data sets nationally, and so the means to conduct this survey was already in place. It also provided elevation data, which I've used to create a height and a slope data set. I found from my research that assumptions on peat density, porosity, and saturation, as well as complicated links between the data and those physical properties in question, are always present, as is the case with many geophysical surveys. So part of this work was to try and tackle this issue and maybe simplify a little bit. So before we get too into the specifics of the site, I'd like to just explain the geophysical methods I've used and why I've used them. So geological materials are naturally radioactive to some degree. In Ireland, radon, as we're all likely aware, is prevalent in many areas, and this is due to the natural decay of uranium in the ground. Other radioactive elements are present in near-surface materials, and the geophysical method of radiometrics aims to measure these. From the animation, you can see that it's a passive technique, so as the plane passes over the ground, it collects the data in the form of counts per second. Much like the frequencies of visible light, elements decay within specific energy ranges, and therefore energy can be selected related to specific elements. These usually include potassium, thorium, uranium, as well as the total counts from within the full energy range. Different materials are composed of different combinations of these elements, and so the method is often used for geological and sediment mapping. As the measurement is collected in counts per second, it does result in an area represented on the surface as the plane moves over the ground. So the next is to why use radiometric data? Well, specifically with peat, radiometric and peat have a special relationship. As peat is made up of organic material, it's not a radioactive source. Secondly, it's very porous, and at least in the northern hemisphere, it usually has a very high soil moisture percentage. Water acts as an attenuator of the radioactive gamma rays. It scatters them and it stops them from reaching the surface. What this means practically is that peat acts as a blanket to any radioactive signal from below. Assuming a constant density, porosity, saturation, the thickness of the peat controls the attenuation of the radiometric signal. So armed with this theory and our freely available national data sets, we can potentially identify areas of similar peat without the need to go in and do a full on-the-ground site survey. So yeah. I'd like now to just show you the site that was chosen for both the Water Peat project and this study. It is a former raised bog in the Midlands of Ireland, and had been harvested by Bord na Móna as an energy source for the local power plant at Shannon Bridge. The image here then shows just a typical life cycle of a raised bog from post-glacial times until recently. So just first, we're starting at the surface. This is an aerial image of the site. It's called Gary Duff Bog and it's located in the southeast of Ballinasloe, just outside the town of Shannon Bridge. The M6 motorway runs to the north, and as mentioned, the site itself is a raised bog, but it's now been cut away, and most of the bog actually sits below the level of the River Shannon, and it's actually pumped to maintain the water table below the surface. Next, looking at the soil map, the Irish Soil Information System classes the site, unsurprisingly, as peat. Surrounding it are alluviums associated with the River Shannon, and find, of course, loamy drifts derived from limestones. Going a little deeper, the Quaternary geology map again unsurprisingly classes this site as cut over raised peat. It's surrounded by glacial tills, river sediments, and even some eskers to the north. It's a very typical Midlands landscape. Finally, the underlying bedrock is described as the Lucan Formation, dating from the Lower Carboniferous period, and has been identified as a uniformly black argillaceous mudstone. And this is just a summary of the site. So, based on what we've discussed, it sort of seems like a relatively simple exercise to take the radiometric data, to plot it over this site, and to point to areas that have sort of similar peat or thin peat. This is just a quick histogram analysis of the data that I've used. So it shows the radiometric data, total counts thorium, uranium, potassium, and then slope and elevation from the derived DEM. It's quite easy to spot the low signal behavior of the data as expected. We can then look at that same data and how it's spatially distributed, where a relatively high signal is highlighted in the lighter colors and low signal in the darker colors. It's not as easy as assumed to see the relationships between the data and to pick out areas of interest or use. This again sort of goes back to my research at the beginning of these methods, which they often rely on assumptions or complicated geostatistical methods to link the data to properties such as density, depth, saturation, or porosity. I decided to sort of take a step back from this and turn to something called exploratory data analysis, where really we start with no assumptions about the site or the data. The first thing I wanted to look for is patterns, and modern machine learning methods are very good at finding such patterns, sometimes are often better than humans. So here I've used a method called self-organizing maps, which analyzes how similar the relationships between the data are and then assigns them to a group or cluster with a similar relationship or a similar characteristic. So here are the same data again, but now divided into 3 groups. We can start to identify which data have relatively high and relatively low signal. So cluster 1, being this side, the green cluster, it has the most complex radiometric signal and is likely interpreted as thin peat, as high signal generally means less peat for it to pass through. It also has the highest elevated and sort of most complicated sloped part of the bog, and there's also likely leaking of signal from non-peat soils outside the boundary of the bog, which I'll show in a second. Cluster 2 can be almost considered like a transition zone. It does have a much lower radiometric signal, but it is still somewhat complex. Here we can say the peat is probably still thin, but it's maybe denser or more saturated. And again, we know the water and increase in density blocks the signal. Cluster 3 has the lowest overall radiometric signal. And it's also the lowest and flattest part of this particular bog. And in this area, we can say that the peat properties or the peat layer properties are acting to block most of the radiometric signal. Finally, then we can assign these groups or cluster classifications back to the locations, the actual data points where they were, and look at their spatial distribution. And what results is a map of the Gary Duff site showing areas of similar peat. This sort of map, straight away, it increases our knowledge of the harvested site. It highlights areas of similar peat that might not have been found without an extensive ground survey. And more importantly, it highlights that, at least from this data set's point of view, that there are 3 main peat types on this site. And these similarities relate to combinations of density, porosity, saturation, and thickness of that peat layer. So this is how I've attempted to simplify things by using machine learning. So we can now sort of bring it back to the initial driver of this study, which was the identification of sites for taking cores for the water peat project. After looking at this map, we decided, or with the engineering department, it was decided to take cores from 2 locations, which were felt to best represent the site. One from the red group 3 and one from blue group 2. We also used this opportunity in the field to do a short ground survey to try and get some ground truthing of this map. And the area for both the cores and, of course, the ground survey is just shown here. The cores are currently being analysed in the lab. However, I can show you the results of the ground geophysics survey. And this is a picture from the field work on the day. We surveyed a swath of about 600 meters along this way, and this is about 30 meters wide. We used an instrument that measures how electrically conductive the ground is. Peat is quite good at conducting electricity, and so we can pick boundaries between peat and other materials quite often using this method. Here now we see a 2D profile with depth on the y-axis and distance along on the x-axis. And the colors here represent how electrically conductive the ground is, with blue being more conductive and red being less conductive. We're able to measure the electrical conductivity of the water in the peat from one of the boreholes, and so put a limit value on what represents peat. And that is the black dashed line that you can see at about 0.5 meters depth here. The relatively pure water in the ground is not great at conducting electricity compared to the peat, and so it can be used as a limiting value. The red area at the bottom of the profile is initially interpreted as the Quaternary sediment or bedrock, and is likely a mudstone or fine-grained sandstone based on the observations on the day and some of the bedrock maps and Quaternary maps shown previously. The red patches at the surface here are actually very dry peat with air-filled cracks on the day, and they acted as resistors to the flow of electricity. The horizontal color bar at the top here shows the group numbers from our airborne map, and we can see that the start of the red cluster here and also in our visual map here does line up nicely with the thickening of peat. as the survey was conducted over an area, we can also look at these data in the form of a map, such as this. So on the screen now is a map of peat thickness taken from the ground survey. This is the thickness from the surface to the base of the peat, which we saw previously. Again, the red group 3 appears to line up with the thickening of peat, despite the scale differences between the footprint of the airborne data and the ground survey. And just to point out here that the peat has similar electrical properties to marl, which was also found in some gouge cores from this area. So it's possible that we're overestimating the thickness of peat here, and it might pull the peat thickness back more in line with the red. We can now, however, despite all that, say with some confidence that our produced map is strongly influenced by peat thickness across the Gary Duff Bog site. So to conclude, and to talk about some future work where we're going with this, is a zone map has been derived for the Gary Duff site using airborne radiometric data, DEM data, and machine learning. These zones are purely data-driven and do not contain any assumptions about the peat. The zones represent areas of similar peat, and so far our investigation have concluded that this zoning factor is strongly linked to the thickness of the peat layer. Future work includes delving a little deeper into these data and into these groups specifically to see if more subtle physical properties such as potentially absolute depth, density, porosity, or saturation could be produced. We also want to possibly incorporate some of the airborne electromagnetic data to see if we can map the sediments under the peat to build a more comprehensive view of the hydrological system overall. And Earth observation data from Sentinel-1, which can model soil moisture changes in the top 10 or so centimeters, could also be incorporated to show the changing surface hydrological conditions in response to environmental conditions such as rainfall. We'll then attempt to put all these, to get all these data to act as input to something called SWOT analysis as part of the water peat project. And finally, of course, we want to see if our methods will work on different peatlands, such as unharvested peat or blanket bogs. So thank you very much, and I'd love to take any questions if there are any.
Dave, that was great. Thank you very much. We have a question from Kuhn.
Yes,
we able to ground truth the results using existing field data on peat thickness, etc., from Bord na Móna?
Absolutely, yeah. So I've recently gotten a peat thickness, a more comprehensive peat thickness map over the whole or most of the site. So that is sort of the next step, is to see how well it ties in. Or sort of what is the relationship between the radiometric data and those peat depths. I just need to verify how and where they came from, because there'd be a timing difference. Like if the peat depth data was from early 2000s and the TELUS data was acquired in 2016, there'd be a difference. So we have to see when the survey was done and then try to tie it to the radiometric data and see what the relationship actually is. Yeah, absolutely.
Okay. Dave, seeing as you're there, I'll ask you a question myself.
Yeah,
I'm curious. I know that Gary Duff, a lot of those Midland bogs, that there is a marl layer at the bottom, you know, because that's what essentially allowed the water to build up in the first instance. Does the marl, and I know it's not probably all that thick, but does it influence that signal?
Very, very possibly, yeah, absolutely. So the radiometric, it's at the moment anyway, it's given an average of what it's seeing. So there could be some influence in the marl included in that sort of depth estimate. So when it comes to trying to get absolute values out, we'd have to take that into consideration, that the marl could be affecting. And it depends what the marl is made up of as well. If there's radionuclides in the marl, they'll act as a source as opposed to a block. So yeah, there's still a good bit to go with this into pulling out absolute values. But as an overall sort of as a data exploration point of view, like we're able to go in quite quickly and make a map of a site that tells us something that we didn't know before.
Great. Thanks, Dave. Appreciate that.
So should I present JP? Excellent.
I think so, yeah.
So thank you, David. That was an excellent talk. Our third presenter for this session, before we go into the poster flash talks, is John Paul Moore, and he will present a talk about representative groundwater flow parameters in complex systems, fractured bedrocks of Ireland. JP, if you're ready, go ahead.
Good morning. Thank you, Fanny, and thank you for the opportunity for the talk. Yes, as Fanny said, my talk today is on representative groundwater flow parameters, complex systems, such as the fractured bedrocks of Ireland. Before going further, I'd like to acknowledge my co-authors, David and Michael, and funding from the EPA and IGRM. Groundwater is a critical resource for sustaining ecosystems and communities. And groundwater in Ireland mainly occurs in fractured bedrocks, in which flow occurs via faults of fracture systems and karsts, also on the limestones. As such, is heterogeneous and complex. with a great deal of uncertainty associated with investigating groundwater in a particular area. Currently, however, bulk approaches to aquifer characterization, including groundwater flow parameterization, are the norm. This is sometimes also in the karstified limestone systems. Later in the talk, we suggest a more pragmatic approach. What do I mean by bulk approaches? Well, the standard approach for groundwater flow parameterization in fractured rocks at the moment is using Darcy's law. Darcy's law is an empirical law derived by Henry Darcy, shown here in top right, in the 1800s. And he was actually trying to purify groundwater for drinking water supply to the city of Dijon. And so he wasn't intended to come up with his sole purpose wasn't to come up with the empirical law, but that he did. And basically, from this experimental setup, he put flow through a sandpack, and then he changed the sands often in the sandpack, and this has a consequence for the law. But anyway, the upshot is that the flow out through the sandpack depended on K, which is the hydraulic conductivity, which I get onto in a moment. But the terms in the brackets here are the hydraulic gradient, and basically that is the water level measured here via these tubes here, and groundwater level measured at the bottom and divided by the distance between them. So that's your hydraulic gradient, and that's the standard measurement in hydrogeological studies in field scale as well. And then this is multiplied by A, which is a cross-sectional area of the sandpack. Now, Darcy put in the value of K, which is hydraulic conductivity, to represent the properties of the fluid that impact how it flows, but also to represent the properties of the medium and how impacted flow through it. And in groundwater studies, we are obviously just dealing mainly with water, so the properties of the fluid are often ignored and are considered constant, and so therefore K, or the hydraulic conductivity, is basically seen as the parameter representing the ability of the medium to transmit fluid. So K is the key parameter then considered for groundwater flow. It's considered the key groundwater flow parameter. Often K is converted to transmissivity at field scale between wells, etc., by multiplying by the vertical aquifer thickness, which is usually assumed to be the vertical length of the wells. So as you can see, this whole approach is a bulk approach. You're assuming that flow occurs, in this instance here on the right, occurs across the entire cross-sectional area. You're ignoring tortuous pathways of groundwater via the pores, connected pores, and the differences in velocities within that as well. And so, but this approach is also applied to more heterogeneous systems, which is and larger scale systems of fractured rock flow systems. And here I've just shown a schematic of 3 groundwater wells in a shaly limestone, just to illustrate how the Darcy law is applied. In this particular instance, I've also shown here on one side of the cube, this is a northwest Cenozoic strike slip faults, which we know in Ireland are the faults associated with the highest groundwater flows. But anyway, when people are investigating groundwater flow in such systems, hydrogeologists tend to use what we call a pumping test. The pumping test involves basically, it's the standard approach where you pump one well and you measure drawdown or drawdown of groundwater levels in all 3 of the wells. And currently, Darcy's law is applied in the analysis of this data. And so basically the average pump rate shown here in Q all over the drawdown delta S is used to provide transmissivity for the bulk volume of rock, a notional volume of rock, which we don't know which it is. But also this is used to estimate a storage parameter. The error associated with interpolating this data to provide a transmissivity value for an unknown volume of rock is usually unknown. We don't know what is the impact of pumping in one well on the wider hydraulically connected system to the wells. And it's for this reason, and also for this reason, but also for other reasons, that we suggest the best approach a more pragmatic approach to analysing a pumping test, for example, or just groundwater levels on their own. We suggest an approach where the measurements at each of the individual wells are taken as the key hydraulic parameters and not bulk parameters between the wells. And I'll show you an example of what I mean by this at the moment. This is a quarry site from County Meath. I'm just showing the outline of the site here in red line. The quarry owners wanted to go deeper in the quarry, and to do so they would actually extract more groundwater, and they wanted to assess what would be the impact on receptors beyond the quarry, such as the river or public water supply well. Initially, the workers came in, they did a cluster of wells in the middle of the quarry, and they did a pumping test, and they analysed using the bulk approach and provided a T value, and they found that they suggested then, based on that, that you have a certain amount of drawdown, which they said will go to the extent of the quarry boundary, or in a bulk way. And basically what they concluded was this was going to be impact on the river or the public water supply. Then later work by Gill and Ball, they went in, they identified F1 and F2, two conductive structures, which is F1 and here in the F2. And then they targeted the trajectories of these faults with loads of wells. And as I said, there's a lot of data here and it's quite confusing, but basically, we've interpreted this data based on the approach that we suggest. So they measured yields from each of the wells. So different colors represent different yields. So the grey represents no yield, blue is poor yield, green is medium yield, and yellow is good yields. But we also interpreted the drawdown, which they conducted a pumping test later on, and they pumped this well here, and we've interpreted the drawdown of that pumping, and we've interpreted that at each of the wells. So we made a different shape of each well based on the amount of drawdown. So there's this star here represents no yield but 15 meters of drawdown. So you can see there's loads of stars around this pumping well. So close to the well there's loads of drawdown, but further away there might be less drawdown. But what you're starting to see here is then from the drawdown pattern is that various connectivity associated with faults. It's the faults that cause the high flows, the yellows, which is the high flows, the high drawdown is associated with the close to the wells, and less drawdown further away. So this borehole up here has high amount of flow, but is low amount of drawdown, so it's less connected to the fault structures close to the wells, close to the pumping wells. So this is a sort of pragmatic approach. Rather than interpreting a bulk parameter, we're interpreting what's happening at each of the individual wells, because that is more representative of the heterogeneous nature of flow in these systems. And many authors have suggested, and it's kind of a standard approach, that basically once you narrow the zone of that you're measuring investigation and into this, isolate a part of a well and therefore perturb or pump or perturb the groundwater levels in just that part of the well, you'll be measuring transmissivity for a smaller portion of the aquifer, and therefore it's more representative to estimate transmissivity, a bulk parameter for that. We actually still disagree with that, even though it's a smaller vertical distance, because you don't know, again, the volume, or you don't know the flow pathways that you're perturbing when you're perturbing that system. And basically, where the difference between our course, people have used and this is what they do here. This is a Packer test, basically. What they call this is a Packer test. They've used Packer tests to obtain transmissivity, whereas we suggest it's the groundwater heads shown here on top and the estimated flows. That's the important data. That's the stuff that you can use to interpret the fracture flow system. For example, this inflection of estimated groundwater flow values coming back down into the well, and this rising head test, so the water's coming back down into the well after the test. This inflection here suggests that you have a zone where the package of groundwater going back down into the well is going through an area where there's larger fracture apertures, larger aperture here causing an increase in flow. So this is a sort of interpretation and characterization that's more representative. In conclusion, flow of fractured rocks is generally heterogeneous and quite complex. So we suggest to focus more on empirical parameters, those measured at the different points. And these will mainly include just the flows, the levels, and the hydraulic connectivity over time and how they vary over time. This approach is more consistent with what people tend to do in karstified flow systems. For example, the analysis of time series and frequency spectrum of time series data, of flow data conducted by Schuler et al. 2020. And our suggested approach, empirical approach reinforces the importance of constraining the geological structure that's controlling flow, the geological controls on flow. For example, the impact of the different structures. Here I've summarized the different structures, the post-Devonian faults and fracture systems, and how they impact flow. The earlier form structures, Carboniferous structures, tend to be sealed, but the Cenozoic faults, the one of which I showed you, and stress release joints, they're conductive. It's the attributes of these structures and their impact on flow. That sort of generic constraints are important rather than estimating bulk parameters for volumes of rocks. Thank you for your time.
JP, that was great. Thanks very much. And really interesting talk. And under time as well. You got in under, you're the quickest so far of the three. So congratulations. You'll get a special prize at the end of the day for that. Just again, so if anyone has any questions, if you want to type them in, and maybe JP, I'll just start off with a couple of things. And you made the point at the end. I think what really is apparent here that it stresses once again the importance of kind of taking groundwater studies away from engineers and handing them over to geologists or geoscientists, because I think there's a real danger that we just look at a geology map and we see it's blue, so it's all limestone, so it must behave in a homogeneous way, or water moving in or on it must behave in a homogeneous way. And I think the relationship there to the karst, I think, is really a good idea, because I suppose we're trying to think about flow in 3 dimensions in the subsurface.
Yeah, I think you're dead right, and I suppose in 4 dimensions because of the time, but
yeah.
you're dead right, Tiernan, and that sort of broader look, evidence-based kind of approach, considering all ways of analysing things, is needed, because they're quite complex systems, aren't they? So so you're spot on in that. You said, what can we take from the geology maps? We have to see, okay, we've the structures interpreted here, what is the lithology, and then take that from there before going into our specific site investigations, where we just have to be a bit more pragmatic, I think, in what we measure, but in what we interpret from the data, because they are quite complex systems.
Yeah, and I suppose following on from that, which immediately is a question from Kuhn Verbruggen, are there implications for water management in quarries in Ireland, and how difficult would it be to apply this method on a wider scale in terms of level of mapping and the drilling required?
Nice question. I think there is implications for the approach to quarry management, because the example I showed, the work conducted by Gale and Ball, that benefited the quarry in the end, in that it was more pragmatic, but in the end it showed there was less impact, because they weren't saying the drawdown was of a smaller area. It was like the drawdown was mainly associated with the pumping wells and associated with the faults then. So the impact was not as considered, and also the direction of impact, the anisotropy, was not as originally thought of when they did the original work. So it does have implications positive for quarry owners. It might seem then that it's more work. If you looked at the data that I just provided, it looked like, oh look, there's loads more work for mainly for the hydrogeologists, and maybe that'll be considered, well, that's more costly for the quarry owner then to have all this extra data analysis by the hydrogeologist. But I suppose if they think about it and they want the quarry work to go ahead, they could think of it in a long-term view, in that, well, actually it might benefit them because it'll give them the go-ahead, when it might give them the go-ahead to extend or deepen their quarry. Just as regard to the second part of your question, I think sort of the pragmatic approach in general is probably a good way to be thinking about groundwater resources and contaminant transport potential in a wider sense. If you're saying, well, how do we approach going into a particular area? I think that sort of a pragmatic approach is probably more beneficial than having any preconceived ideas. So in that sense, yeah, I think it can be used in that way.
I hope that answers the question, Kuhn. And I suppose as well, if we tie it back to Jim's talk and even to what Dave was talking about, it gives us some idea that, that there's great potential for the TELUS data to give us some sort of sense, even to get some sort of sense of what the structures are at a more local scale, that could be used for targeting drilling rather than just putting a raft of boreholes across a quarry floor. And then I suppose as well, ultimately, with the machine learning kind of techniques that Dave was talking about, there's possibility there, I suppose, to even think about how can you distribute parameters away from a bulk scale, but to more localized scale. Yeah.
Yes, exactly. So considering the evidence at the different scales and different types of evidence, it's critical, and the TELUS data provides a lot of excellent data in that regard, both in the large scale that we never would imagine before. So yeah, definitely, I think you're right. That can definitely be brought in when considering particular investigations.
We've another question from Brian McConnell. How can you make predictions of groundwater flow at depth? This is in particular in relation to geothermal exploration below sort of site investigation range.
Again, you'd start off, and is it Brian McConnell or Brian Connell?
No, Brian McConnell.
Brian Connell.
McConnell.
So I don't want to make sure I'm not telling someone who know his own knowledge. But anyway, you'd start off with what are the map's geology constraints and the map structural constraints, and then you consider and so the broad impact of the difference. Then once, if you have any field data, then you constrain whatever field data you can get if you have outcrop or quarries nearby. But the generic constraints I showed regarding the impact of different structures is important. Do you have normal faults in your area, carboniferous normal faults, because they tend to be sealed, but they might be karstified depending on the lithology. So and so the trends and directions of the different structures, the attributes of different structures is important in a generic sense. But then when you get into the field, you just have to see if you have quarry and outcrop available, can you tie this into your map data or your TELUS data? And then there is a depth dependency to different structures, like the joints occur very close to the surface, and they're much lower densities below that. So you can use those generic models as in starting off. There's a decline in density and connectivity of joints with depth, for example. That sort of generic constraints can be used starting off, and then you'll have to conduct your specific site investigations after that. But using the map data and the TELUS data and to come up with a broad structure of the area, and then any site data are available, then you bring that in, and then you sort of interpret what, and then you'd have to conduct your maybe your drilling or your hydraulic testing just to back up your geology model. That's a sort of pragmatic approach.
Good. Okay, JP, that was great. And it brings us up just about to 10 o'clock. So,
okay.
Fanny, do you want to wrap up the session, the first bit?
Yes, sure. So thank you. I would like to thank the speakers for 3 very nice talks, very informative, and everyone who joined. And now Brendan is going to take over so that we can start the poster session. It looks very good, so, you know, stay put and support the students on this virtual IGRM. So that will take us, so that will start now at 10 and it will take us until 10:30, where we're going to have a break. And Tiernan has to go, unfortunately. You were the best co-chair I could ever ask for. And yeah, we'll just wait for Brendan there and start with the poster session. He said that already, as soon as a poster slide will come up, the author of the poster is going to start presenting. Okay, thank you.
Hi everyone. My name is Emer McKenna and I am a final year undergraduate finishing out a geology degree at University College Cork. This is my project on the Carlingford Igneous complex in County Louth. So the Carlingford Igneous complex is characterised by bimodal magmatism, a layered gabbro intrusion and a cone sheet swarm. So the main purpose of this fieldwork was to produce a detailed geological map showing the spatial distribution of each lithology, which you can see on the slide here, understand the construction of the complex, and produce a 3-dimensional model. So petrographical investigations such as Raman spectroscopy mapping were used to detail the accessory mineral budgets of the ascending gabbro layers and detail the mineral phases of each layer. From the combination of data, it became possible to produce some cross sections, which you'll be able to see on my poster, and give an interpretation of the geological history. So the deduced intrusion sequence is first granite, followed by the gabbro intrusion, and then lastly the cone sheet swarm. However, multiple phases of felsic magmatism happen throughout the gabbro intrusion, resulting in the coexistence of mafic and felsic magmatism. And then 4 distinct gabbro units have been identified. You can see them here in the map from the different shades of green. So within each layer, there is evidence for modal and rhythmatic layering, with each unit being defined by an olivine and augite ridge base, moving upwards into a plagioclase ridge top. And finally, the many inward dipping mafic sheets form a cone sheet swarm and are expected to be in place from varying sections of a stratified magma chamber, which is centrally located. So this was a really great project in place to do my undergraduate project. I would really recommend anyone going up there for a look around. It's a really lovely part of the country. So that's just a very quick summary of my project. I really hope you've enjoyed, and thank you for listening.
Hello, I would like to share my screen as I have a video prepared timed for 2 minutes, so I will try to do this now. Right. I'm trying to find, yeah. I think I can try with this.
I think she just left. Oh, she just joined the meeting again. so maybe we give her a bit of time.
Hello, can you hear me? Hello.
Yes.
Yes, I had audio problems earlier. I had to already leave the meeting once and rejoin you. I don't know why, but yeah, I will try it again, and maybe from the or maybe can you just show it and I'll just gonna talk. That's probably, yeah. Hopefully you can hear me. Can you hear me? Yes, okay. I can't see anything shared on Teams, unfortunately. So, okay. But if you can see it, it's fine with me. Can you see it? If I send you the video, can you play it if I email you? Okay, it's loading. Yeah, I can see it now. Thank you. So my name is Alina Primrau. I'm a research fellow based in Botany Department, Trinity College, Dublin, working on the larger DAFM-funded PROTECT project. And today I'm presenting insights into preliminary procedures for estimating pesticide risks in Irish grasslands using HARE 2014 tool. The goal of this work is to refine HARE 2014 tool using Irish data. This includes pesticide usage surveys, Irish climate, land use, soil properties, and other inputs in order to model pesticide risk indicators for soils in Ireland. HARE is a tool that can calculate risk indicators related to agricultural use of pesticides. It has a number of built-in terrestrial risk indicators, among others also for the acute risk indicator for earthworms, which is used in this presentation, and you can find more further details in the poster. The work to refine HARE 2014 for Irish conditions includes upgrading or refining several databases, and refinements were already done on spatial or geodatabase, on climate data inputs, and on assigning the crop calendar regions for Ireland in HARE. These regions are specific for HARE and are needed for internal calculations. After introducing these refinements, the simulation test runs were then performed by temporarily using very general inputs shown here, if you can see it, for glyphosate active ingredient for Irish grasslands. However, further refinements on this are still needed and are planned for the future, including building of compound database with other active ingredients in addition to glyphosate. So for now, the grassland map was obtained from another model, the PERSIM model data maps, and the other inputs for which are needed to run the HARE model, such as for soil properties, are still used from HARE default databases just assigned to the new grid. And both of these will need to undergo further refinements in the future. These test simulations then generated initial output for glyphosate acute risk for earthworms, which is presented here. And this map-like output shouldn't be confused with the final risk map, because further improvements are still planned for the future. So the goal of all of this work is to actually have a functioning HARE 2014 tool refined for Irish conditions, which will be able to generate outputs that will inform an area-based risk assessment and will provide the basis for developing recommendations for potential future soil monitoring and sampling needs in Ireland. Further details can be found in the poster. Thank you very much.
Yeah, can you hear me? Okay, my name is Roisin Mooney and I'm a final year Earth and Ocean Science student at NUIG. My project is on a new Pedalodus fish fossil that was found in Ballybunion. Pedalodontiforms are an extinct clade of marine cartilaginous fish which first appear in the Carboniferous and go extinct during the end Permian mass extinction. Each family in the order are distinguished from one another by their dentition. Pedalodontiforms have a distinct pedal-shaped crowns with deep roots and are known today from isolated tooth specimens. This is why TCD 31087 is unique, as it is extremely rare to find so many teeth so close together. This fossil was found in an old coastal quarry south of Doon Point near Ballybunion town, and it's Brigantian in age. It was scanned using a micro CT scanner, and TIFF files were uploaded into spheres where 3D models were then created. The well-preserved teeth of morphotype 1 were mainly used to identify the species as Pedalodontiform. These teeth are pedalodus-like in shape, with a distinct wide triangular crown and thick roots. This placed the specimen in the family Pedalodontidae as the genus Pedalodus. Morphotype 2 has no distinct features and are likely older teeth that are no longer in use and merged together to form a solid buttress, which works to support the functional teeth. Morphotype 4 is likely a juvenile tooth that is not fully developed, that may have grown into an adult tooth over time. The number of cristae seen in the models and the similarity of the tooth shape to those in the literature likely places these teeth as belonging to Pedalodus ohiensis. The curvature of the teeth are thought to either accommodate tooth stacking as part of a whorl, or to allow for opposing teeth of the opposite jaw to slide past one another during biting. TCD 31087 has 3 teeth of morphotype 1 that are stacked together and in the same orientation. This limits the accommodating space for the opposing teeth and supports the idea that the teeth are part of a whorl. Thank you for listening.
Yes. So shall I start? Yeah. Okay. Thank you everyone for joining in. I am working at University College Dublin as a research scientist in the School of Earth Sciences. I'll just give a brief introduction of what we are trying to do in this study. As you may know, the overall goal in reflection seismology is to image the subsurface. And we can do this by applying a seismic source at the ground and recording the corresponding signals at multiple ground locations. The recorded signals will have contribution from many wave types, but it is the reflected waves that are of prime interest, as these contain information about the interfaces separating the various geological units beneath the ground. Unfortunately, these reflections are usually masked by high amplitude surface waves, particularly in onshore surveys, and are only partly suppressed by a suitable survey design. Therefore, surface waves can be considered coherent noise, and to image the subsurface, we need to remove these waves from the reflection records. As the title of this poster suggests, seismic interferometry is one way to accomplish that. In simple terms, seismic interferometry provides a recipe for generating a virtual signal at a given receiver. The signal is virtual in the sense that it is not generated by a real source, but rather obtained by cross-correlating signals at 2 receivers, with one of them acting as the virtual source. So for example, if we have 2 receivers, and if we were to cross-correlate the ambient noise recorded at these receivers, we can get the signal that would have been generated at one receiver had there been a source at the other. If the considered pair of receivers was surrounded by many sources in 3 dimensions, the recovered seismic signal would actually contain all wave types. However, because of the limited source coverage, only partial wave field is recovered in reality by interferometry. In land seismic surveys, for example, where all the active sources are either on or close to the ground, mainly surface waves are recovered. This feature is actually advantageous to us because we can condition the recovered surface waves and adaptively subtract them from the recorded data. So in this poster, we have proposed a methodology on how we can successfully accomplish this task. And you're welcome to have a look and feel free to ask any questions. Thank you.
Yep, can you hear me okay? Perfect. Hi everyone, I'm Avery Fenton. I'm a final year student from NUI Galway and completing my undergraduate degree in Earth and Ocean Sciences. With this project, we are taking the first look at the microvertebrate assemblages at St. Brendan's Well in County Clare. The intent of this study is to better understand the paleo environment at the time of deposition for the Magauna and Slieve na Gleasha formations. Limestone samples were collected from 3 horizons and brought to the lab for processing. Acid was used to extract the fossils from the limestone matrix, and the remaining residue was filtered by size and dried in preparation for picking. What the results of the picking has shown us is that there is an uneven distribution of biodiversity and fossil abundance across the study beds. The Slieve na Gleasha formation is overwhelmingly more biodiverse and produced the vast majority of total fossil specimens. The Magauna formation yielded significantly fewer specimens and less variety of species. However, the presence of xenocants in these beds is what begins to unlock our understanding of the paleo environment. Xenocanthids were a group of fish that are evidently eurohaline and able to move between a wide range of salinities from freshwater to marine, making them an environmental indicator, which is countered by the dominance of conodont material throughout the formations that indicates a definitively marine environment. Based on these findings, it appears that the Slieve na Gleasha formation was likely deposited in a deeper outer shelf environment, while the Magauna formation was deposited in a shallower coastal area. If there are any questions, please feel free to get in contact.
Yeah, I'm here. I think it's the full posters. Oh yeah, it's just showing up for me there now with that screen. So hi everyone, my name's Kevin Duffy. I'm also in final year in NUIG, and my final year project is the identification of the so-called Jarrow microsaur as being of the Nectardine order, and specifically Characterization galvani. And so this specimen is NMS 1967.13.2 from the National Museum of Scotland. And this specimen was previously identified as being a microbracket from the Jarrow coal seam assemblage in County Kilkenny. And specimens such as these, they are often, as old as these, they are often subject to significant flattening, compression, deformation, and this one is no different, which has made identifying features in the past to be difficult. However, with the use of CT scanning, we are able to find far more features than was previously possible. And in this project, I used the program Serial Paleontological Image Editing and Rendering Software, SPEARS, in order to create a 3D model of the skull of NMS 1967, which you can see in the poster here. And the interesting thing about this specimen is when looking at the vertebrae, we can see that we have the vertebral centrum and then a fan-like neural spine, which is far more indicative of nectardines than it would be of microbrackets. And this re-identification of the Jarrow microsaur as Characterization galvani is significant because previously this was the only known specimen of a microsaur from the Jarrow assemblage. But now with this revelation, there are no known microsaurs from the Jarrow assemblage, only nectardines. And if anyone has any questions, feel free to get in contact with me. And thank you very much for your time.
Yeah, I'm here. Good morning, everyone. I'm Jess. So my slide here is definitely more of a teaser for my poster, so I hope you'll go look at it afterwards. This is about my postdoc I completed last year with ICRAG at NUIG. It was just a one-year project entitled Trust and Perception, Key Challenges Facing Geoscientists in Practice and in Irish Society. And the aim of this project was really to explore the public perception and the trust in geoscientists and the perception of geoscience as a subject, kind of with the application to improve science engagement and communication. So we carried out this project through a series of semi-structured interviews with various stakeholders, including some geoscientists, and we followed that up with an online survey then as well. And the survey was formulated using statements extracted from the interview transcripts. So as you can see here from this figure, trust is quite strong in geoscientists. We've compared it here to other scientists, especially some that interact with the natural environment as well, just to see a comparison. But there is a significant level of uncertainty about trust in geoscientists as people and what they do. And this existed both within people who had a geoscience background and those who had no geoscience background. So that was a really interesting result, that there's a certain level of uncertainty around the trust, both within and outside of the community. In terms of the perception of geoscience, people had a fairly good idea of what the subject was and what people might do. However, as we can see from some of the quotes here, there is a significant lack of clarity around the application of geoscience. So you can see here on the left, I'm sure there are benefits, I just don't know exactly. And on the right here, geoscience doesn't have a strong image in my head. So we're hoping that the results of this survey, which you can go and see on my poster, will, as I said, better inform science engagement and communication around geoscience issues going forward. So my contact details are on the poster, and please get in touch if you've any questions or would like to know any more about the project. Thank you.
Yep, can you hear me? Great. Good morning, everyone. My name is Amy Benim. I'm a final year student studying Earth and Ocean Sciences at NUI Galway. For my final year project, I looked at the relationship between rainfall and volcanic eruptions by analysing historic eruption records and precipitation data. This project was supervised by Chris Bean at DIAS and Tyrion Henry at NUIG. So there's a relatively large body of work that seems to establish that rainfall can trigger eruptions. Most notably, there's a recent paper that determined that the 2018 Kilauea eruption was triggered by extremely heavy rainfall in the weeks and particularly in the days leading up to the eruption. The picture on the slide, it's a bit dramatic, but that's from the 2018 eruption. So my project was then focused on establishing a statistical-based method to see if it's possible to detect this relationship using low-resolution, easy-to-access data. And this is then with the view of applying this method to a broad range of volcanoes. My initial results, I think they still need a lot of work to kind of firm them up. There's some interesting results from the Klyuchevskoye volcano, which is a volcano in the Russian Far East. And my poster, it just outlines a bit of background to the project, my methods, and those results from that Russian volcano. So if you have any questions, suggestions, any comments, anything at all, my email is there on the slide and it's also at the end of my poster. So thanks very much.
Hi, yeah. Hi everyone, my name is Orla Tyrrell. I'm in the final year of my undergraduate degree in geology at University College Cork. And my research poster focused on the work I undertook for my final year project up in Glentraston in Connemara and under the supervision of Dr. John Weeby. So just to get an idea of where I was, you can see from the satellite map there, Galway City is down in the very southeast corner. And if you follow the white road along the coast, that's the main R336 road from anyone from the area. And where it goes up north towards Mam Cross, Glentraston is pinpointed in red there just off the main road. So you could quite easily drive right past it. It's a very small agriculture focused village with a population of about only 50 people. On my main map there, it's located pretty much smack bang in the middle. But geologically speaking, it's a very interesting area. So the village itself is located just on the contact between the northernmost boundary of the Caledonian Age Galway granite batholith, and where this comes into contact with the older mid-Ordovician age igneous intrusives, namely an epidote-rich gabbro unit and a quartz diorite unit. So for my project, it was mainly a mapping project. I covered roughly 14 square kilometers in field of largely igneous metamorphic lithologies. And then research aspects, I was really interested in looking at the different types of magmatic fabrics in the area. So namely solid state quartz ribboning and also megacrystic alignments, and how these varied and transitioned from one to the other in the different areas, and how this reflected the magmatic processes that occurred over time. I also had a look, as you can see on the east, there's a major fault running through the area. This is the Shanawona fault. I look at and analyze the different interactions around this fault zone. And then as well, the main batholith itself, I kind of tried to break this up into different units to better understand the different phases of magmatism. And I did this by looking at the subtle changes in textures and mineral assemblages within the main batholith. So all these results for my project are expanded on my main poster, and my contact details are there as well. And happily welcome any questions sent my way. Thanks very much.
Yeah, thanks very much. This is my second year being involved in this conference, and I was just thinking to myself, a lot less hungover this year around. But yeah, so I'm up at Queen's University in Belfast, looking at the impact of thermal plumes on properties of the Stone Aquifer. Yeah, it's like a year and 4 or 5 months into the research now. Lost a bit of time there due to the COVID, but I got a time to actually look at other sides of the project in relation to policy and things as to why like geothermal technology in general on the island of Ireland isn't necessarily where other places in Europe are, which was great. So it's given me good motivation to carry this project out so that hopefully in the future we can see more industrial geothermal projects. So yeah, we're looking at basically re-injecting the Sherwood sandstone with warm plumes of water. Where the project is at the moment is EGS came over from England just before Christmas there, and did some BMR logs, so borehole magnetic resonance of the Sherwood sandstone. So it was really great to get that data, because how the porosity and permeability values are going to be impacted by these warmer plumes, we're not so sure yet, because we think we may see some secondary mineralization and organic growth and precipitation and things like that. So it was great to get those logs done. I'm in the middle of analysing those, and also working on fee flow, the DHI groundwater modelling software. Believe it or not, I'm actually dialed into Berlin on another screen here on a fee flow course. And it's really interesting. Looking forward to incorporating the BMR data into my model, the 3D model for the site that we have at Queen's with the 3 test wells drilled into it. So yeah, just watch this space. Moving forward in the year, we're going to be going into our thermal injection tests and monitoring with the distributed fiber optics. And yeah, looking forward to seeing how the aquifer reacts to the thermal plumes. Thank you very much.
My name is Sean Houghton, and I am on the disposition of rainfall. My name is Sean Houghton and I am a final year undergraduate student at the Department of Earth and Ocean Sciences at NUI Galway. This project focuses on the assessment of catchment characteristics and stream flow dynamics on the Barna River in County Galway. The Barna catchment is a small ungauged catchment located 5 kilometres west of Galway city centre. The catchment area borders the western city suburbs and marks the transition into rural peatlands to the northwest, which mediate a relatively complex flow regime. As part of my final year thesis, the overall aims of this research were to collect flow data from across the catchment, to assess the impact of catchment characteristics on the disposition of rainfall and system response times, and to use statistical analysis to determine the magnitude of flood and low flow events. A combination of field techniques, statistical analysis, and assessment of previously published data were utilised to determine the catchment characteristics and the nature of the flow regime. The associated poster highlights some of the findings of the research with particular focus on the importance of stream flow data and the effects of land management practices on flow regime dynamics. I hope that you find the results interesting. Please feel free to get in touch should you have any questions, and thank you for taking the time to be here today.
Hello everyone, this is Larissa Oliveira. I'm here to give you a brief introduction about my poster, which relates to the use of 3D data in advancing seabed mapping techniques for deep water habitat classification. So cold water corals are complex structural habitats. They are considered biodiversity hotspots in deep sea environments. As most of marine ecosystems, they are subject to several climate and anthropogenic threats. Based on the importance of cold water corals, this research focused on the application of underwater photogrammetry to improve the classification of cold water coral reefs, especially on the Porcupine Bank Canyon, which is the largest submarine canyon in Ireland, and is also a special area of conservation. 3D photogrammetry is a computer vision method that uses a principle called structure from motion to extract information from a set of overlapping images at various angles to reconstruct complex scenes and recreate 3D models like the one you can see here in the video. We want to do this because cold water corals are naturally 3D structures, so we believe that mapping them in 3D can give an accurate representation of the real habitat in comparison to traditional 2D methods. So in this research, we developed 3 classification workflows implemented in image analysis software, and so far, 2 of these workflows had only been applied to terrestrial data. So it's the first time that they had been applied in deep sea environments. So the dense clouds are manually annotated by an expert into 2 classes, coral and seabed, and the percentage distribution of coral and seabed samples from the annotated dataset showed that there is an average of 7.2% of coral and 92.8% of seabed. On the right side of the poster, you can see the output classification of each method, along with a pie chart of the distribution of coral and seabed from the manual annotation. From all these methods, we could see that the accuracy on the multi-scale geometrical classification was higher, but all the methods are suitable for the wider marine scientific community. When comparing the 3D methods with the Obaya method, we could see that there is a difference between class distributions of 0.2%. So this shows that there is a potential impact on using 2D methods to represent objects that are naturally 3D. So we would like to conclude that cold water corals can significantly contribute to deep sea biodiversity due to their 3D structure and heap reef building capacity, and also that the workflows provide an original and not yet applied methodology for the classification of 3D reconstructed marine environments, especially at the Porcupine Bank Canyon. Thank you.
Okay, that is the end of the poster flash talks. I would like to thank all of the participants in today's session, our 3 main speakers, our 2 session chairs, and all of our poster flash talk contributors. If you would like to look at the posters, you can find them all on the conference website, mic.ul.ie/. IGRM-2021. All the posters are up there online for everyone to see. Our next session is going to start in just under half an hour at 11 o'clock. So I hope to see you there. Okay, thank you very much to everyone who has been watching, and we'll see you in the next session.